In this video, we're going to begin to take a look at exponential functions. The form of an exponential function, but basically the equation looks like, will be y equals something times some base raised to the x power. So the key thing is that the x is in the exponent place. A lot of times this a value will be something like 1, but it does have some control over what happens with the function. And some applications to being plugged into, particularly when we begin looking at some of the word problems. So let's take a look at one of the most basic exponential functions, y equals 2 raised to the x power. So if we begin looking at a chart, say like with x's and y's, if x is 1, let's say when x is 0, 2 to the 0 power is going to be 1. If x equaled 1, y is 2. When x is 2, y is 4. When x is 3, y is 8, so on and so forth. Okay? So what begins to happen when I plot this out is this 0-1 combination is very popular with a basic exponential function. Then it's 1, 2, 2, 4, 3, 8. So we begin having the graph go up. If we begin looking at negative values, like -1, 2 to the negative first power is 1/2. -2 is going to be 1/4. You'll notice there's never a value of x which will make the function turn into a negative number. So if we begin to graph those, 1/2, 1/4, okay? What'll end up happening is a graph forming something like this. Okay? Key parts is this approaches 0, goes towards 0, or for the y value. Here, the y value increases rapidly. And that's important to recognize in the sense of these exponential functions, is that they do increase very, very, very quickly because of multiplying exponentially. Okay, that's the fact that the exponent is increasing. Let's take a look at how a couple other things change sort of the equation. So the first thing, let's take a look at what happens when we change, if we're looking at y equals some b raised to some x power. How does changing the b value change the graph? So what I've done is graph three numbers in general to see if we can try and kind of do a trend. What's important to realize here is that by increasing sort of what that base is, 2 to the x is the widest, 3 to the x, 4 to the x. The important thing is that when b is greater, okay, as the b gets larger, it gets more narrow. And the reason why the graph gets more narrow is because it increases much more quickly. So it rises very much more quickly. Okay? Whereby the opposite is true. If the b is less, okay, is lower, it's going to be less narrow. In other words, more wide. Which we see illustrated by this graph. Another example of how changing the equation changes the graph. What are the reflections? Let's go ahead and do that. So the first type of reflection is something called the reflection across or over the y-axis. Okay. This is where I take a look and say, okay, well, if I have y is equal to 2 raised to the x power, let's change that to y equals 2 raised to the negative x power. The placement of the negative sign right in front of the x causes this change, that when I have a graph looking like this here, we're going to mirror it so then it becomes like this over here. It is a reflection that if at any point I were to examine and look and say, okay, How far away is this from the y-axis? I would have the exact mirror off to the left-hand side. Same thing down here. Okay. The most crucial point, once again, is the point where they intersect, and here is at 1 because neither graph is moved at all. Okay, so this is what's called a reflection across the y-axis. Next, we're going to take a look at the reflection across the y-axis. If you may have guessed, if I start with y is equal raised to the 2x power, the reflection across the x-axis is given y equals negative 2 to the x power. In this case, the negative sign, in sense, applies to the whole function, applies to the y value being changed, which means it's a reflection across the x-axis. In a sense, the x value hasn't changed, it's the y value that changed. So let's look at the diagram. And here you go, kind of using the same principle as before. If this is this far away from the x-axis, then I have the mirror being true on the opposite side. The x-axis acts like the mirror that reflects what is up here with what is down below. It's kind of like if I were to fold the paper along this x-axis here, the two graphs would line up perfectly. So these are what are called the reflections. The reflection across the y-axis, the reflection across the x-axis for the most part. Okay. The next thing we're going to look at are translations. Translations are when we move it left or right or up or down. So let's talk about translations. So we say it's a translation by however many units, and we always say the direction left or right. Okay, so let's look at an example. And so this is one example where I would say this is a translation by 1 unit to the left, or a translation left by 1 unit. The reason I know that this is left and not up or down or anything else comes from the equation itself. The x plus 1, where it had been x, is going to be what's essential. And with the x value, it's going to be the opposite of whatever it says. So if it says plus 1, it means I'm actually going to go to the left one. The reason being is because the setup is x minus, okay, is going to be kind of what's essential. Think about when we did slope and the equation was, x minus x1. It was always with kind of subtraction in mind. So then this negative 1 is where the it's going to be to the left one. So, and if you can see this on the graph where the blue is the second one. The important thing is where y equals 1. In that case, it's negative 1. So it takes this and shifts it to the left one. So it's the whole entire graph is actually shifted to the left by 1, which kind of makes sense as well. Okay, that when x equals 0, originally, it's 0 plus 1, which is 2 up here. When x equaled negative 1 originally, well, negative 1 plus 0 is going to be 2 to the 0 power, which is going to be 1, which is going to be right there. Okay, so this would give me a translation to the left by 1. Okay, let's take a look at the right. This is a translation to the right by 1. Once again, if I find where x or where the y value hits 1, it is going to be when x equaled 1. And the key part here is since it's 2 raised to the x minus 1, once again, this tells you that it's to the right 1 unit. In looking at translations up or down, it's sort of reminiscent of the fact that in order to change the y, we would have y minus 2 is going to equal that 2 to the x. In order to put it in function terms, of course we're going to add the 2 to both sides. So y would equal 2x plus 2, which is then what we see up top here. Okay, about how it changes. So anytime I have a plus 2 You'll notice that it's at the same level as the base, not in the exponent of the x plus 2, x minus 2, or x minus 1, x plus 1, as the previous examples. And what you'll notice here is it takes this intersection at 1, 0, at least at this level, and shifts this up 2 spaces to be here. Okay, so this is a translation up. By a similar example, in order to shift something down, so once again I've got my standard 2 raised to the x power, y equals 2x to the x power. In order to bring that down 2 units, I have 2 raised to the x minus 2. So what you'll notice is it drops it down 2 units, shown once again by that minus 2. So for the translations up and down, it operates how you would think about it with the plus 2 and the minus 2. The translations left and right would be the x minus 1 and x plus 1. It would be happening as part of the exponents by the x value. One thing I would like to comment a little bit on, especially as we look forward to exponential growth and exponential decay, is what is the role of the a value? We said that the form of the equation was y equals a times b raised to the x power. We've talked a lot about what happens here with b to the x. The a value is generally what the starting amount is. How much of something do you begin with? It will also cause that 1, 0 point that we talked about as the y-intercept. It will cause that to shift as well. It'll either bring it down to like 1/2 or 1/4, or it'll push it up larger depending on what this value is, because it multiplies b to the 0 power, which is 1, times the a value will give the y-intercept. B is what the function is, in a sense, multiplied by. It's used a lot of times in a word problem. So something like this. Suppose 30 flower beetles are left undisturbed in a warehouse bin. So that is going to be my starting amount. The beetle population doubles each week. And then I want to know how much is left after 30 days. So the key part here is it doubles each week. So the 56 days we need to treat. How many weeks is that? Well, 56 divided by 7 is going to be 8, so it's going to be 8 weeks is the value what I want. Okay, after 8 weeks. The first thing we need to come up with is the function. So y is going to equal my starting amount of 30, and since it doubles each week, I use 2 as my base, and then x as my time. Sometimes I'll use t to represent time. So it's going to be my time in weeks. So in this case, what I want to know is y is going to equal 30 times 2 raised to the 8th power. 2 to the 8th power is going to be 256. So I want to know what 30 times 256 is, because 2 to the 4th is going to be 16. 16 times 16 is 256. So 256 times 30 is going to give me the fact that in 8 weeks I'm going to go from 30 flower beetles to 7,680 flower beetles. And imagine what that would be in another week if it were 9. Okay, so it increases very, very, very quickly. This is just when x equals 8. Okay, so this is an example. This is actually something we're going to work on a little bit more in the next section, but it's good to begin to get sort of a flavor and idea of this.